Good morning. Today we discuss what is a Varactor diode. Many circuit applications employ the voltage variable properties of a reverse bias PN junction. A PN junction designed for such a purpose is called a Varactor, which is a short form of variable reactor. A reverse bias depletion layer capacitance is given by Cj, which is proportional to Vbi plus Vr to the power of minus n, where Vbi is a built-in potential, or we can say the Cj or the reverse bias depletion capacitance is proportional to the reverse bias to the power of minus of n. Here Vr is very much greater than Vbi. N is equal to 1 by 3 for linearly graded junction and n is equal to half for an abrupt junction. Thus the voltage sensitivity of C, the capacitance, the variation of C with Vr is greater for an abrupt junction than for a linearly graded junction. We can further increase the voltage sensitivity by using a hyper-abrupt junction having an exponent n greater than half. Here we have a figure which shows three dropping profiles of P plus N junction with donor distribution Nd given by B as a function of x by x0 to the power of m, where B and x0 are constants, m is equal to 1 for linearly graded junction, m is equal to 0 for an abrupt junction, and m is equal to minus 3 by 2 for an hyper-abrupt junction. The hyper-abrupt profile can be achieved by epitaxial growth techniques, which we know is a layer by layer deposition of atoms. To obtain the capacitance voltage relationship, we use the Poisson equation, which is given by d square psi by dx square is equal to minus b in brackets x by x0 to the power of m. If we integrate this equation twice with appropriate boundary conditions, this gives the dependence of the depletion layer width on the reverse bias. So the depletion layer width W is proportional to Vr to the power of 1 by m plus 2. Therefore, Cj or the capacitance is given by epsilon s by W, which is proportional to Vr to the power of minus 1 divided by m plus 2. So we will get n is equal to 1 by m plus 2 if we compare these two equations. For hyper-abrupt equations with n very much greater than half, m must be a negative number. If we choose different values of m, we can obtain a wide variety of Cj versus Vr dependencies for specific applications. An interesting example shows that in the case for m is equal to minus 3 by 2, for this case n is equal to 2, when this Varactor is connected to an inductor L, a resonant circuit, the resonant frequency varies linearly with the voltage applied to the Varactor, as we have shown over here in this equation. Here Wr is equal to 1 upon under root of L into Cj, and it is proportional to 1 upon under root of Vr to the power of minus n. So this is equal to Vr for n is equal to 2. This is the value of the resonant frequency of the resonant circuit. Now we discuss what are the current voltage characteristics. A voltage applied to a PN junction will disturb the precise balance between the diffusion current and the drift current of electrons and holes. Under forward bias, the applied voltage reduces the electrostatic potential across the depletion region, and this we have shown in this figure. The drift current is reduced in comparison to the diffusion current. We have an enhanced hole diffusion from p side to the n side and electron diffusion from n side to the p side. Therefore, minority carrier injections occur, that is, electrons are injected into the p side whereas holes are injected into the n side. Under reverse bias, the applied voltage increases the electrostatic potential across the depletion region, as is shown in the middle of this figure. This greatly reduces the diffusion currents, resulting in a small reverse current. In this section, we will consider the ideal current voltage characteristics. We then discuss departures from the ideal characteristics get due to the generation and recombination and other effects. So first of all, we will be discussing the ideal characteristics. The ideal current voltage characteristics based on the following assumptions, that is, the depletion region has abrupt boundaries and outside the boundaries the semiconductor is assumed to be neutral. Second assumption is the carrier densities at the boundaries are related by the electrostatic potential difference across the junction. And the third assumption is low injection condition, that is, injected minority carrier densities are small compared with the majority carrier densities. In other words, the majority carrier densities are changed negligibly at the boundaries of neutral region by the applied bias, and neither generation nor recombination current exists in the depletion region, and the electron and hole currents are constant throughout the depletion region. So the departures from these idealized assumptions are considered again afterwards. At thermal equilibrium, the majority carrier density in the neutral region is essentially equal to the doping concentration. We use the subscripts N and P to denote the semiconductor type and the subscript O to specify the condition of thermal equilibrium. Hence, NN0 and NP0 are the equilibrium electron densities in the N and P sides respectively. The expression for the built-in potential can be written as VBI is equal to KT by Q ln PPP0 NN0 divided by Na square. So this is equal to KT by Q ln NN0 by NP0. So the mass action law, that is PP0 NP0 is equal to Ni square, has been used. So if we rearrange these, we will get NN0 is equal to NP0 e to the power QVBI by KT, and similarly PP0 is equal to PN0 e to the power QVBI by KT. So we note that the electron density and the hole density at the two boundaries of the depletion region are related through the electrostatic potential difference VBI at thermal equilibrium. So from our second assumption, we expect that the same relation holds when the electrostatic potential difference is changed by an applied voltage. When a forward bias is applied, the electrostatic potential difference is reduced to VBI minus VF, but when a reverse bias is applied, the electrostatic potential difference is increased to VBI plus VR. So the equation can be written as Nn is equal to Np e to the power Q VBI minus V divided by KT, where Nn and Np are non-equilibrium electron densities at the boundaries of the depletion region in the N and P sides respectively, with V positive for forward bias and negative for reverse bias. For low injection condition, the injected minority carrier density is much smaller than the majority carrier densities. Therefore, for Nn is very much greater than or equal to Nn0, substituting this condition, this will yield the electron density at the boundary of the depletion region on the P side, that is X is equal to minus XP. So Np is equal to Np0 e to the power QV by KT, or Np minus Np0 is equal to Np0 e to the power QV by KT minus 1. So Pn is equal to Pn0 e to the power QV by KT. Pn minus Pn0 is equal to Pn0 e to the power QV by KT minus 1. At X is equal to Xn for the N-type boundary, we show the band diagrams and carrier concentration in a PN junction under forward bias and reverse bias conditions respectively. We note that the majority carrier densities at the boundaries minus XP and XN increase substantially above the equilibrium values under forward bias, whereas they decrease below the equilibrium values under reverse bias. To define the minority carrier densities at the boundaries of the depletion region, these equations are the most important boundary conditions for ideal current voltage characteristics. Under our idealized assumptions, no current is generated within the depletion region and all currents come from the neutral regions. In the neutral N region, there is no electric field and thus the steady state continuity equation, this will yield to d square Pn by dx square minus Pn minus Pn0 divided by dp tau p, this is equal to 0. This is the continuity equation. The solution of this equation with boundary conditions and Pn is equal to x at infinity is equal to Pn0, this will give us Pn minus Pn0. This is equal to Pn0 e to the power qv by kt minus 1 e to the power of minus in brackets x minus xn bracket close divided by Lp, where Lp is equal to under root of dp tau p is the diffusion length of holes, minority carriers in the N region, At x is equal to xn, Jp as a function of xn, this is equal to minus q dpn by dx at x is equal to xn. This will give us q dp pn0 divided by lp in brackets e to the power of qe by kt minus 1 bracket close. So similarly, we obtain for neutral p region np minus np0 is equal to np0 e to the power of qv by kt minus 1 e to the power of x plus xp bracket close divided by ln, and jn as a function of minus xp, this is equal to q dnp by dx at x minus xp, this is equal to q dn np0 divided by ln e to the power of q by kt minus 1. Here ln is equal to under root of dn tau n, this is the diffusion length of the electrons. The minority carrier densities will be shown later. The graphs over here in this diagram, they illustrate the injected minority carriers recombine with the majority carriers as the minority carriers move away from the boundaries. The electron and hole currents are shown at the bottom of this figure. The hole and electron currents at the boundaries have been discussed earlier in those equations. The hole diffusion current will decay exponentially in the n region with diffusion length Lp, and the electron diffusion current will decay exponentially in the p region with diffusion length of Ln. The total current is constant throughout the device, and that total current is given by J, which is a sum of individual currents, Jp as a function of xn plus Jn as a function of minus xp. This gives us Js e to the power of qv by kt minus 1. So Js is equal to q dp pn0 divided by Lp plus q dn np0 by Ln. Here Js is the saturation current density. This equation is called the ideal diode equation. The ideal current voltage characteristics is shown diagrammatically in the diagram over here. Here we have shown the Cartesian and the semi-log plots. The first one shows the Cartesian plot, second one shows the semi-log plot. In the forward direction with positive bias on the p side, for V is greater than or equal to 3 kt by q, the rate of current increases is constant, and for every decade change of current, the total voltage change for an ideal diode is 60 millivolt. This is equal to 2.3 kt by q. In the reverse direction, the current density saturates at minus Js, as we have shown over here in this diagram. And so, thank you.